I enabled it, Mark. I think he's showing recording.
Okay, yeah, that's good. Okay, so then go ahead.
Okay, as Mark mentioned, we just show a few of our integration concepts, probably one candidate per type of integration. The first one, let's imagine the customer or anyone else has defined requirements for your system, and as you may know, there's this requirement interchange format, so a file-based integration. There are several, or the typical kind of integration we have in Medini is this import from something. So as Mark mentioned, safety projects are critical to have a certain baseline or a certain revision of requirements or whatsoever information in the project. So having them or referring to a certain revision is essential. So we typically import data or proxy of data into our project. This one is meant to import requirements from a RecRF file. So you typically export this in other ALM or PLM systems as an interchange format. Let's take this requirement file here. We have then a new model for requirements. As you can see, just a few of them were imported here. I may now go ahead and change a few things in my tool. For example, reject some of these requirements and now go ahead and export this back to a RecRF file and pass it back to the person who gave me this RecRF file. And that person then again may import that one into his system. So that's one version. The other one is a more tighter integration of ALM, PLM tools like PDC or DOORS. So I also could go ahead and export these requirements directly to Integrity. What we are using here is a native or proprietary API of PTC Integrity. Unfortunately, I cannot show this now because the Integrity server is down for maintenance. Anyway, you can imagine that this one just pushes the requirements into the PTC Integrity. The main issue here is that these different to standardized APIs like OSLC, these tools like PTC are very dynamically structured. So customers which are running these kind of software tools as ALM, PLM systems can define arbitrary types. So a requirement is not always a requirement. In one project, it's completely different than in another project. So a heavy dynamically mapping of attributes and types is essential part of this import-export mechanism. Same holds, of course, for DOORS and any other of these kind of tools, which is also for us, I think, an important point in this project. So standardization is okay, but this kind of mapping attributes and meaning of semantics of what an attribute of a requirement, for example, is all about, is essential. Next, I would like to show us that we have seen that we have the SysML modeling inside of Medini. Typically, these SysML models already exist in other tools, so we just can go ahead and import these SysML models either from Enterprise Architect. So this is again a file-based approach. Internally, these Enterprise Architects are database files which you can analyze and import into our own SysML format. So you can see I have more or less import the structure of this Enterprise Architect file. Everything which is not of interest for us or which we do not support, like use cases or actors, we just skip during this import. Same holds for Rhapsody. Maybe I can show this here. So here's a short example of a very simple Rhapsody structure model, which I am now going to import. Again, we are using a proprietary API to import from Rhapsody, which is a very complex SysML tool. So they have their own file system structure. Anyway, this allows us here to have now the Rhapsody model inside. Maybe one information, I can now go ahead and restructure this model a bit on my side. For example, I don't like how the originator of this tool organized the separation of blocks and parts here. So I could go ahead and move these types into a separate package because this is more adequate for my safety analysis. I could then go ahead, just to show that as well, to derive an FME worksheet for this specific types I have imported here. Could go ahead and say, okay, I have several ports here, and this crash sensor may create a stuck at failure mode, which is then later on used in my system FMEA. I could then go ahead and change the Rhapsody model, add some more ports, for example, to the sensor, and re-import that here. That means the importer is able to really handle modifications on both sides. So the SysML model may change in the Rhapsody, but it may also change on my side. And the importer is able to do a real merge of the changes and allow the user to either keep local changes or drop them and fall back to the system model I've imported from Rhapsody. Last integration I would like to show is the mentioned task management integration. So the tool is not only used to do safety analysis, but also to execute reviews and audits based on these functional safety projects. Typically, companies have also systems for this in place. That might be, again, something like PTC integrity or bug tracking systems or Redmine systems, as you like. Might be even Google applications in the cloud. So we use the Eclipse Myelin technology here to abstract from external task management systems. So this architecture foresees that there are connectors per different type of external system, and then you can go ahead and bidirectionally link these tickets, which either are created during an audit or something else, and link that to an object in the project, either requirement or structure element, or vice versa. Just create tickets while you analyze the system. For example, just go ahead and say that certain elements here need to be changed. Here this is not connected, but let's move back to this item definition of the electric signal log. If I don't like this, what the safety engineer has done, I just create a new ticket and could push this back to the ticket system. It's annotated in a SysML model, and I can later do a review and checking whether these tasks have been really fixed by the safety engineer, and that way have it later on the record what the history of the review and changes in my project. Mark, just a question. Shall we give it back to you, or just go ahead and show quickly the team support as well?
I would think that you should show the team support, because we just have 4 or 5 minutes left, and then this is for the aspect of how multiple people can work together, because this is also a thing that we want to improve in AMASS, that they have a more seamless way of cooperation. But maybe you can first show what is already existing. Yeah.
Okay, what you probably have to know, behind the scenes we have a file-based approach. So all these models here, which are shown in our model browser, are in-memory representation of EMF-based models. Behind we have a file-based approach that automatically means that just one person can work on these files, and we use external revision control systems to have a version history. If 2 people are working on the same project, meaning on the same file version, we provide a compare and merge approach to help these people working together. That means each one is working on its separate branch or copy of this project, and in order to bring this together later, we need or we support this by just offering a comparison. So you may say, I want to just compare this with any other project, or if this is version control, with any other revision in your history. I have here a separate project which has small modifications, potentially executed by a separate person or even by me in history on another day, or it's from another company coming in. So I just go ahead and say I want to compare these 2 projects. And then we compare the EMF representations of these two models and represent the changes in diff tree. You can go ahead and analyze the differences of the individual objects here closer. So for example, I had assigned an ASIL B to this safety goal, while the other person had assigned an ASIL A, which of course is propagated further down here. So you can see I had created a separate functional safety requirement, which the other person did not have, and so forth. So in the hazard and risk assessment, I had assigned a specific E4 value, while they had rated it with E3, which results in the different ASIL. So this is just an example how the approach of working with multiple persons on a same project using a file-based approach is currently working. As you could imagine, that this is not in favor of all persons. So persons which are used to use version control systems, they don't have a problem with this approach. People which are not used to this, but typically working on databases, not caring about versions or whatsoever, typically have some problems using this approach. Okay, this is not just a compare. Just to mention this, you also have merge capabilities here, so you could either partially or completely integrate changes done by some other persons. That allows you to pass or substructure the activities you have to do in your safety project. For example, one person is doing the fault tree analysis, another person is doing the hazard and risk assessment, and then later on integrate that into a single project, or at least check the derivations of the different persons having working on this one. Okay, Mark, I think that should do.
Okay.
Mark, are you still there?
Yes. Can you somehow give me back the host role? Is that possible? Because
sure.
I would need that to pass the ball to the next presenter.
Okay.
Okay, I'm the presenter, but still not the host, right?
Yeah, I'm still the host. I just keep this running and just mute my microphone.
Okay, so Jan, then you would have to push the ball, I think, to Stefano and Laura from Intex.
Okay.
Because they will then show us the next tool, which is chess.
Right, yes. Okay, so thank you. So, Stefano Puri from Intex, and Laura Baracchi, my colleague, is here with me. And we will present the chess tool. So chess is not, I have to say that the chess is not only a tool, but it is also a methodology, and offers also a modeling language for the development of software system for high critical.
Hello, Stefano.
Yes.
Do you plan to share your screen?
Yes, I'm going to share. Okay, so I will introduce chess through some slides, just because I think it's important to understand the methodology which is implemented by chess, and then I will move to the tool support, and I will show you some features currently available. So chess, okay, this basically was a result of Artemis GU project, and okay, several partners from Europe was involved, and this slide summarizes the objectives of chess. So as I said, the goal is to provide a methodology for development of software system based on component design approach, and we the focus is to allow the users to the software system by using a component-based language, and be able to provide extra functional properties for the component, and be able to analyze the properties with some specific analysis of the modeled software system, and then finally generate code. So we also support the implementation part for the design system. And okay, so as apart for what regards the language, we based on the OMG support. So we implement our modeling language by basically by defining profiles upon the OMG UML and other available modeling languages from OMG. Okay, I think I can skip some details, and okay, this slide is about, as I said, the modeling language implementation, which is basically a tailoring of UML, XML, and master. And also we provided, so we will provide support with master for what regards the modeling on the real-time property for components. And then we defined a new an ad hoc dependability profile for what regards the modeling of dependability property of the components. And then we rely on the UML for what regards the functional specification of the component, and we rely on XML for what regards the specification of the system view, because we also, on top of the software modeling level, we also, the chess methodology also allows to design the system view, so to allow to take into account other concerns from the software part, other concerns not strictly related to the software part. And so for the system view, we basically rely on the XML. And here also we add some extension related to the control-based support, but I will show you this in the presentation. And I think, okay, one more slide. Yes, it's important to understand the component model of chess. So basically, when you model it, so here I'm talking about the software part. So basically, when you model in chess software component, you have to first of all design the component and model the component from the functional point of view. So you also so you have to define the component out of any particular context by specifying its provided and required functional interfaces. This is basically the UML part. And then on chess, when the function specification of the component is available, chess allows to decorate the functional interfaces faces of the component with the extra functional attributes, so in particular with timing and dependability attribute and timing and dependability property. One advantage of this approach is that it is possible to reuse the same functional specification of the component in different contexts where different extra functional properties are required. And the other entities which play a relevant part in this component model are the so-called entities containers and connectors. So these entities are responsible for implementing the extra functional properties that the modeler attaches to the component functional interfaces. So basically, the container is you can think about the container as a wrapper, which is in charge to implement the functional property of the component itself. itself, and then the connector is a kind of entity which allows use, which is in charge to implement some extra functional or quality of service property concerning the communication of the components. So just to one more slide to conclude the presentation, then we move to the toolset. Okay, this is basically a summary of the chess methodologies, so with different modeling steps. Some modeling steps are performed manually by the user, others are performed automatically by using a model-driven approach, so by using automatic transformation. So the flow, the main flow is the following. First of all, the user starts to model the software component. Here again, I'm focusing on software part, so I'm leaving the system view support aside for the moment. So for part regarding software specification, the modeler so designed the software component by using the chess component model support. So specify the functional components and decorate the functional specification of the interface of the component with the extra functional properties, and this information is part of the PIM model, the so-called platform independent model. So here we are at the level which is abstract for a specific platform implementation. In parallel, the user can describe the platform, so the hardware components where the software part will run. And we also can provide on the deployment view. The user can provide the information about the software to hardware, to processing resources for allocation. When the user, so here, when we are on top part of the process, so when the user specifies all this information, it is possible to perform model transformation to generate a so-called PSM. So basically in the PSM, of a specific model, the tool and the methodology creates automatically the container and the connector entities that I talked to you about on the slide before. So the entity that will are in charge to realize the answer function information of the components modeled in the PIM. Starting from the PSM obtained model, we are able to perform some analysis. I will show you some kind of analysis later. So the analysis are performed on the PIM, so for instance regarding scalability analysis. The results are back propagated to the PSM and then to the PIM level, so in order to allow the user to see the results in the space where he works, so at the PIM level. So the user doesn't have to touch the PSM and look at the PSM model, but just he and she can work on the PIM level. So the analysis results are made available, and when this process can be reiterated several times until the results of the analysis are satisfactory, and then once the analysis are okay, the design is okay. Starting from the PSM, the user can generate the code for the design. So in this, by doing this, chess offers so a model-driven support for the analysis and code generation, and a current by construction approach that allows to obtain a code which is aligned to what has been currently analyzed at the model level. So I think this is all for what regards the introduction of the chess methodology and the component model language. So if you have any question, you can interrupt me, or otherwise I can show you the tool. I have 15 minutes. So, but I think it was important to introduce the chess methodologies first, because it is important to understand what is behind the tools. So I will show you an example of a chess model. Again, here we start from a software model. So this is also, okay. For what regard the toolset, we rely on the Papyrus editor. So we have implemented on top of the Papyrus editor the implementation of the chess language. So basically, as I said, the chess language is a profile of UML marked as XML. So we have implemented this profile in Eclipse, and particularly by using the Papyrus UML editor. So I know that there will be a slot dedicated to the Papyrus tool demonstration on Wednesday, if I remember well. And so I would avoid to give you the details of the Papyrus editor here, but just I will focus on the customization that we made in order to support the chess methodology. So, and what can you see here? So, okay, I can briefly introduce the chess model on the right, on top left side of the screen. So here you can see a tree view of the chess model. You can see here several sub-packages. Basically, each package here represents a view defined by chess methodology, where it's possible to model specific concepts. For instance, a requirement here, system entity in the system view. Then we have the component view, where it's possible to model software, so the software components with the functional and extra-functional specification. Then we have the deployment view, where it's possible to model the hardware platform and the software to hardware allocation. Then we have a view dedicated to the analysis. So this analysis allows the modeler to specify any input which is required to perform a specific analysis beside the information already specified in the other views. And then we have the PSM view, which is is automatically generated. So the entities here are automatically generated by model transformation. And this view is a read-only view, which is used by the tools in order to perform analysis and code generation. So I will start by giving you some example of what is possible to model in the component view. So let me start. So let me follow a typical process, modeling process in chess. So as I said, in chess, for what regards the software, you have to specify the component from a functional point of view. So basically here we are using the UML, so it is needed to specify the functional interfaces of the component, and then it is possible to model a component, software components. And in chess we have two kind of components: a component type, it's called a component type, and a component implementation. The component type is only about the specification, the functional specification of the component. So here you only put the information on the provided and required ports, basically interface ports, and whether the component implementation is a component which provides an implementation of a particular component type. So the component implementation is something that provides implementation behavior for the provided operation. When you have modeled the component implementation, you can instantiate the component implementation in a given software system. And so I can show you here a software system already modeled. So here we are using the UML, so a composite structure diagram to model the software system. So these are instances basically of the component implementation you have modeled. with the functional specification as provided and required interfaces port. When you have done this, you can decorate, as I said, the functional part of the operation with the extra functional information. So, for instance, we can use and rely on the Marte support. Okay, we have extended it to Marte in order to overcome some limitation. But basically, for instance, here we can see how it is possible to decorate the functional specification of an operation exposes through these ports with the timing related information, like for instance the worst case, the fact that the operation has to be called sporadically with a given minimum interval of time. We can define here the deadline, and so you can specify extra function information for all the component interfaces, and this is for the timing perspective. So when you have, for instance, filled all of this information for the timing perspective, you can perform schedulability analysis. In order to perform schedulability analysis, we need to define the so-called analysis context that allows to run the schedulability analysis. So basically, the analysis context refers to the components and the platform you want to analyze. Now I avoided to run the analysis due to time constraints, but here, for instance, you can see what once you run the analysis. So we perform the schedulability analysis, and then the information are back propagated here at the model level. So here you can see for instance, the response time, worst case response time value for each operation decorated with sporadic or cyclic. So this allows to perform and retrieve information from the schedulability analysis. Besides the timing information, just also, as I said during the presentation of the slides, support the dependability profile, and for instance, we offer support. So let me briefly open another diagram. We, for instance, just it's possible to annotate the component support with the expected failure in inputs, and then using it's possible by using the dependability profile. I can show you something here. Okay, this is a model, and a different model made by Chess, where it is possible to use the dependability profile to specify some failure in input to the system, and then attached to the component you can specify some failure propagation rules by using a formalism made by MDH. So MDH defined this support. So here you can, for instance, decorate the component with some failure propagation rules, and then attach some failure in input to the systems, and invoke the start and execute the failure logic analysis to check how the failures propagate between the different components. Okay, this is another analysis that we support in Chess. So in this case, we are using our dependability profiles. Maybe I can show you briefly. The failure propagation are provided. Okay, maybe it's not here. Okay, I can. Okay, if here, for instance, you can see how a given, in this case, a given component instance has an extra functional properties which declares the failure propagation rules between its input port and output port. So in this case, we can use a formula, the language specified by MDH. Okay, so I have time. Okay, I think I can switch to the other kind of to a new item which regards the contract support, which is I think also relevant in AMASS. So for this I have to okay, I open a different model. So in chess, in xSAP we extended the chess modeling language to introduce the concept of the contract for a component. So we defined at the modeling level an extension of XML that allows to model contracts and the association of contracts to components. For instance, this is an example which models a given system. Here we are in the system view, inside the system view of chess. So basically here we are modeling not just software entities, but entities of different disciplines. And okay, here basically we are using the XML, so subset of XML. What we support in chess is the definition of contract. So contract is basically an aggregation of two entities, of two properties, the assumptions and the guarantees. In chess, the assumptions and guarantees are modeled as formal properties. So formal properties are, so you can think about formal properties as a kind of formalization of some requirements or some properties that express the behavior of a given component. So in chess, it's possible to specify the assumption guarantees of a contract in any language. We don't force the usage of a particular language, but we support. We have an integration with the OCRA tool from FBK from FBK. So if the user uses the support from FBK to specify the contract specification, in particular the assumption and guarantee specification, then it is possible to use the chess to OCRA integration. So once you have defined a contract, you can associate a contract to a block or a component, and you do this by using the so-called constraint here, the contract property. So you take you instantiate this property to the block and type the property with the contract. Okay, this is the contract that you want to associate to this particular block. So basically, you instantiate the contract to the different blocks. This allows you to reuse the same contract in different blocks, because here we are working with instances of contracts. For a given contract, you can specify if the contract is weak or strong. Okay, but I can skip this. And then for a given contract, you can specify how a contract is refined. So basically, here you can see that this block is decomposed into sub-blocks. These sub-blocks have also a contract instantiation, so I have the contracts associated. So in chess you can say how this contract is decomposed by the contracts of the child blocks. And you you model the contract refinement through this window. If you fill the model with this information, so contract association to components or blocks, contract decomposition, information about how a contract is decomposed, and then if you specify the assumption guarantees by using the Otello language that which comes with the OCRA tool, you can perform the formal verification of a contract refinement in chess. The chess perform this analysis by automatically invoking the OCRA tool. So chess transforms the chess model in a corresponding OCRA model, and then invokes the OCRA tool, and then the results are back propagated again at model level. So we will see the detail. You will see the detail of the OCRA tool analysis in the next presentation. Okay, one more thing, one more feature I can say is that we also support an import from the Medini tool that we have seen before. So in order, okay, so here I have to, enable the automatic property, because I would like to show you just the command that allows to import the model from the Medini tool. So by doing this, you can select the Medini tool, and just allows you to import the Medini model into the chess model. So we have implemented this integration in context of the Sedemo project in order to make the integration from Medini, which is more focused on the system level part, and chess, which is allows you to specify more in detail the software parts and also allows you to generate the software implementation. So I think I've run out my slot, so if you have any questions, otherwise I can move we can move to the next presentation.
Okay, thank you very much, especially for also being in time. So I hand the ball now to Stefano from FBK, right?
Yes, please.
Yeah, okay. So, so you should have it?
Yes.
Great.
Now you should see my screen.
Yes.
So I'm presenting the OCRA tool, and then my colleague Marco will present the xSAP tool. The idea behind the OCRA and the contract-based approach that we support was presented in a previous phone conference, so you can find the slides regarding the sales results in the SVN, and also you can find more documentation online. So I will focus the tutorial on the usage of the tool. So OCRA can be downloaded from the online web page, ocra.fbk.eu. Is publicly available for non-commercial purpose, and we have an ongoing development, so an internal version since last public release was done 1 year ago. So for the project, for the AMASS project, we will internally release new updates, so we have to agree where which means to use for the releases, and we will use on purpose license for free usage by industrial partners during the project. So here you can download the tool, which is a tarball containing different files, including so once you uncompress the tarball, you will have different files, including the user guidelines and the binaries for different platforms. Online you can find also more documentation, like different the user manual, different papers and presentations. For example, if you look at this presentation, is the most recent one, and more or less contains topics that we already seen in the presentation in this web seminar organized for AMASS. So the idea has already been presented also by Stefano from Intex, and is to support contract-based design in which you decompose the architecture into subcomponents, enriching each component specification with the contract in terms of assumption and guarantees. And each assumption and guarantee is specified in a temporal logic, as we will see in a moment. This tool has been integrated in different higher level modeling frameworks. Besides chess, we integrated in autofocus, that is a tool developed by Fortis, and in Compass, that supports a variant of AADL. So during the AMASS project, we will focus on integration with chess to integrate further functionalities and to improve the integration. So now I will pass to so the idea is that you can use this modeling framework as front end, and there is a model-to-model automatic transformation to interact with the OCRA as backend. So typically these tools interact through files, generating the input file for OCRA and receiving as in response some verification results that are then mapped back to the user. So I will instead show the input language of OCRA, which is a textual representation of the architecture. So in OCRA you specify the components in terms of an interface and an optional refinement. So in the interface you declare the input and output ports. For example, in this simple example, I have an input event and an output event, and you declare the contract. For example, here I have a main contract in which I assume true, so I don't have any constraint on the environment, and I guarantee that whenever I receive the input I, this implies that in the future I will respond with an output O. And please interrupt me anytime with the question for clarification. So in this component I have also refinement. So this component is decomposed into subcomponents of type simple. The simple declaration is below. And you declare also the connection. So for example, the input of S1 is connected to the input of the parent component. The input of S2 is connected to the output of S1, and the output of the parent component is connected to the output of S2. And the contract of this component here is refined by the contracts of the two subcomponents. And in this very simple example, the subcontracts of the subcomponents are the same for the parent. So whenever I receive an input, I respond with the output. So if I have a change of reaction, so whenever the system receives an input, this is connected to the input of the first subcomponent that is propagating the output to the output port O, that is connected to the input of the second subcomponent, that then propagates the output to its output port O, that is connected to the output of the parent component. So OCRA provides a scripting language to perform different kind of analysis. So you can specify this commands in a script like this. For example, this is a very simple script to check the syntax, and you can call the tool from command line to check your input. For example, here I'm invoking this script, this simple script that checks the syntax on the example that we have just seen, and it provides textual output, and we have also XML output for the different verification functionalities. So, for example, I can also check the refinement of this I can check the refinement of this example with the OCRA check refinement command. So I can call from command line this second script to check the refinement, and it generates internally 3 proof obligations. One, to check that the subcomponents entail are a good implementation for the parent, so entail the contracts of the parent component, and one proof obligation for each assumption of the subcomponents to ensure that the assumption of subcomponents is entailed by the composite environment surrounding the subcomponents. So, for example, if I can inject a bug in my example, so for example, in the system I require instantaneous reaction, while in the subcomponent I have a possible delay in between input and output. This will result into a violation, and the tool will generate a trace, an execution trace, showing the violation of this property. The trace is a sequence of assignments to the ports and alternating with the event specified in the OCRA specification. So we can also implement the diff components with a behavioral description. So OCRA actually has 2 modalities. You can use a discrete time semantics or a continuous time semantics. In the discrete time semantics, we use SMV for describing the behavior of components, that you can think of as a symbolic representation of a state machine. So, for example, I can specify the behavior of this component in this SMV file, and this basically declares a local variable. Besides having the input and the output ports connected to the component specification that are declared here, it also declares a local variable location. So this component can be in a wait state, in location, or in the send location. And here I declare the initial state, so initially it's in the wait location. and I declare then the transition. So whenever I'm in the location wait and I receive an input, then I don't produce an output, and I instead go to the send location. And in the send location, I generate an output, and I go back to the wait location. While if I'm in the wait location and I don't receive an input, sorry, I will stay in the wait location. And this also can be generated by the chess. You can specify the state machine again with the state machine diagram, and this is automatically generated by the tool. And then I can check with another script if this implementation is correct with regards to the contract specified in the OCRA input. So I can run this check from command line. And the tool runs in background new XMV, the model checker, to check if this behavior satisfies correctly the contract specified in the input OCRA file. You can also extend the model with more complex for example, with the more complex specification. In particular, we can also support real-time contracts, like those shown by Stefano in the chat demo. For example, here I'm not only saying that I is followed by the output in some point in the future, but I specify that the time until I output O is less than 2 time units. And for example, this can be then refined by the contract of the subcomponent, in which the delay between input and output is less than 1 time unit. And so you can see that you can budget the maximum delay of the parent with the contracts of the subcomponents. So we can also check this second example with OCRA, and also for this it generates the proof obligation, and it checks if all proof of obligation are valid. So in this case, the refinement is correct, which I remind you means that whenever you plug an implementation for subcomponents, and this is correct for the local contract, the composition of the components will automatically entail the construct of the parent component.
Partially, per esempio, questo è partially, no?
So we can also extend the specification with the more complex contracts. I mean, I just specify very simple contract for the purpose of the demo. Online you can find more complex example. We have a case study with on a wheel braking system that consists of 30 components specification and hundreds of instances with different and much more complex contracts.
True.
By the way, Laura, I can hear you. Yes, this is just for a very simple, just to show an assumption that is not true. For example, I can assume that whenever I have an input, in the next step I don't have again the same input, and in order to this can be exploited by the subcomponents. So this is the same assumption here. So indeed entail by the parent assumption, and then the assumption of the second component is entailed by the assumption of by the guarantee of the second subcomponent that is now strengthened. So it's no more just ensure that I have the reaction from input to output, but also ensure that I don't have two consecutive output. And again, I can just I can also check this kind of refinement. So now you can imagine that things can get more complicated, and so we can also some contracts that are more and more complex, and so we can we want to validate this specification. So maybe these temporal formulas contain some inconsistencies or do not reflect what we have in mind. So we have some requirements, some analysis on purpose to validate the specification. So, for example, we can validate that all formulas are so we can call this validate command here. For all contracts, if the formulas are consistent and it produces an execution trace that is compliant with the contract. So you see here, of course, that all contracts are okay. And also we can check if these guarantees here are compliant with because for example here the witness that I was receiving for the consistency was saying simply that nothing happened. So the contract the execution trace is trivial. So then I want to check if actually are consistent also with the tracing which in the future have an input. And I can check also this, and the tool will produce an execution trace before in which I receive an input and I also have an output. So here you can see that the output is immediate, instantaneous in the same transition of the input, and so I can specify more complex scenario in order to have more complex execution. And in case there may be cases in which the scenario is not compatible. So, for example, here I'm checking if these two guarantees are compatible with the scenario in which always but in my last example, if you remember, I specified that not have two consecutive output. So in this case, the tool will say that is not possible, and moreover we will provide an xSAP core showing the reasons for consistency. So in particular here it shows that this part here of the contract is consistent with my problem specified here. Okay, as functionality, we also provide fault tree analysis, so we produce a fault tree automatically from the contract specification. Basically, we inject automatically failures in the subcomponents and in the environment of the system, and we automatically generated the dependency among the fulfillment of the contract and the failure of subcomponents or environment. So, for example, in this case, this contract may fail if one of the subcomponents fail in guaranteeing this contract. So we have a command also for this, so OCRA compute fault tree, and we can call this computation on this very simple example, and we automatically generate and we can, for example, view what has been generated in a graphical view, simple fault tree in which the system failure depends from the OR of the subcomponent failure. So, as I said, we have discrete time and continuous time support, so we can also declare a continuous variable that evolves continuously in time. And we also instead integrated this contract-based specification with a tool for automatic of a model-based specification. So this was a quick check. So basically, in this use case, we had a specification of the end-to-end protection specified by AutoSAR, contract specifying this protection. And the AutoSAR also provide a state machine for the check of the end-to-end protection mechanism. And this state machine was model checked again the contracts that are and the contracts are refining the system level contract, and the state machine is used to automatically tests for a C implementation of this component. Finally, I mention some recent results that we developed in a project funded by the European Space Agency. This was in the framework of Compass, where OCRA is integrated with the Compass for verification. Here, instead of besides the possibility to provide to specify assumption and guarantees components, we also provide a mechanism to specify the contrast and the properties with the attributes for the components. So for example, here I'm just saying that I have a predefined property for the input for the input take picture that automatically produce a reaction to say that I have a property for the max delay, and I specify 5 seconds, and these attributes automatically internally generate corresponding formal property that a similar property similar to that I showed in the textual study. And so this may use the specification of properties without requiring to know the temporal formulas syntax. And yes, this concludes. So we had the on this tool, and we will continue the development in AMASS. If you have questions, I will pass the ball to Marco for the xSAP part. You have any question?
Thank you very much. And the next speaker is Marco, right?
Yes.
So I try to pass the ball there. By the way, I'm very sorry for this kind of wake-up noise which we have here in the line, but I don't know how to cancel this, so I'm very sorry.
Okay.
Marco, I think you have to unmute. We can already see the screen, but we cannot hear you.
Okay, here we go. Hi. So good morning, everybody. So I have some slides introducing xSAP. Then I will also show a live demo of the tool. So xSAP is a platform for model-based safety assessment. We have used it in several projects with aerospace and avionics companies. We have some ongoing projects, for instance, with the European Space Agency and also with Boeing. So the project started in 2002, and at that time there was an old tool called xSAP. So xSAP is basically the new generation tool which replaces xSAP. Currently, the latest release has been is out since March this year. As for OCRA, we have free licenses for non-commercial applications and for academic purposes, and of course we will make suitable licenses available also to the AMASS partners. We have a website. So on the website xsap.fbk.eu, you can find more information about the tool, you can download it, and so on. So I'm going to use a simple example to demo the tool. It's a redundant system called battery sensor. The idea is that we have 2 batteries powered by 2 generators, and these batteries feed some sensors, and the sensors produce some output. The system is redundant, so you have 2 batteries and 2 sensors, and the connections between batteries and sensors may be changed depending on possible faults. So the 2 generators may fail, and also the two sensors may fail. In case of a generator failure, you can, for instance, switch and feed the sensors from the battery that is still okay. And we assume that the system is alive, provided that at least one of the output sensors is okay. So this is the xSAP flow. So we have here we specify the input models. We have a nominal model which describes the system when faults are not present, and we have some fault extension instructions. Basically, the idea is that we can get the specification of the faults from a fault library, and we can specify which faults we want to inject and the effects of the faults on the nominal model. And there is this block called model extension, which automatically generates the extended model. Extended model, so both the nominal model and the extended model are in assembly language. And so the extended, you can use the extended model to run quite some analysis. So you can do fault analysis, FMEA, and some other stuff. So this is the analysis part of the flow. So I'm going to demo at least fault analysis and FMEA. And if time allows, I can also show something about TFPGs. So TFPG, time failure propagation graphs, are a formalism to specify fault propagation and to make analysis like diagnosability, fault detection, fault isolation, and recovery. So let me go to the demo. So first of all, I want to say that we have some editors. Based on xtext, they can be embedded in the Eclipse environment. So we can visualize models. This is the nominal model corresponding to the battery sensor. So if you like, you can navigate it. So for instance, this is the module which implements the generator, and it has there is this variable that says records whether the generator has power or not. This is the module for the battery. So the battery, for instance, has one input from the power generator, an identifier which is the 1 or 2 depending on the battery, a mode, and this is just the time, and so on. So this is SMV code. And similarly, in addition to the nominal model, you can specify using this language the faults that you want to inject in the model. So for instance, here we are specifying that for the module generator, we want to inject a fault called the generator stacked force, which is an instance of this fault stacked force taken from the fault library. And this is permanent, so we can specify whether the fault is either permanent or transient, and this is the probability of fault. This is just a parameter instantiation, so basically we are saying that the stacked value is false, and that the input variable which is affected by the fault is the S-power variable, and again also the output is the same variable, S-power. So the idea is that the S-power variable will be stuck at value false when the fault occurs. Similarly for the sensor, we can inject stacked false fault. And finally, we can also specify common causes. So the idea of common causes is that you may have events that break the independence of faults. So in this case, for instance, we are specifying that we have a common cause called CC1, which affects all the module called of type generator with a stacked force. within 1 to 10 time units. So this basically means that if CC1 happens, then both generators are affected within this time span. So they both fail within this time span. So let me go to the demo. So xSAP can be accessed both from the command line. So we have a command line similar to SMV, to SMV command line, but we also have some Python scripts that encapsulate the most used functionalities. So I'm going to demo the two using the Python interface. I have pre-typed some commands just to speed up the demo. So the first thing I want to demo is the model extension. So we have this command called extend model. This is a Python script called extend model. It takes as input the nominal model, which is an SMV model, and the default extension file, the one that we have just seen. So if we run the command, it will generate the extended model, which is again an SMV model, and a specification in XML of the faults. So these files will be then used for doing the analysis, like for the analysis. So if we run, for instance, for the analysis, so we have this dedicated script called compute fault tree. It takes as input the extended model, the specification of the faults, and then there are some options. In this case, I'm going to generate the fault tree with probabilities and also with symbolic probabilities. And this is the event, the top-level event, which we are using for this analysis. Not is alive, which means that the system is not alive, that is, both sensors do not produce any output. So if I run the command, the fault tree is generated. It is contained in these two files, events and gates. It's in 40 plus format. We can view it. So we have this graphical viewer to view the fault tree. So basically in this case, as you can see, the top-level event may be caused either by combinations of faults of the two generators or of the two sensors, but also we have these single points of failure, which are given by the two common causes. As you can see, so we have these probabilities at the leaves, which we have specified in the input fault extension information. And of course, the probabilities of the intermediate events and of the top-level event are generated automatically by the tool. As I mentioned, we also have the possibility to compute the probability in symbolic form. So we can generate it either in MATLAB format or in Python. So this is an example of the MATLAB code. So as you can see, it's a function which takes as input the probabilities of the different faults and of the common causes. So we have these parameters of the function, and then in the body we compute the probability of the top-level event. So this function computes the probability of the top-level event, which is defined as x per 21, which is then defined by the previous expressions. So the idea of this symbolic probability is that you can compute it for different values of the input probabilities, and you can also generate charts like this one. So you can, for instance, plot the probability of the top-level event depending on the probability of the generators, for instance. And so you can get different graphs depending on the values. And you can do a similar thing in 3 dimensions. So for instance, here we are plotting the probability of the top level event depending on the probability of the generator failure and the probability of the implementation error, and so on. So this is just to give an idea of what you can do with the symbolic formula. I can also show you that you can generate FMEA tables. So we have this script called compute FMEA. Parameters are similar to the usual ones. In addition, you can specify the cardinality of the FMEA table. I'm using the very same top-level event, not is alive. If I run it, the FMEA table will be generated, and this is the FMEA table for cardinality 1. So we only have 2 single points of failure, the 2 common causes that are possible explanations of the top-level event. But if you like, you can generate the FMEA table with, say, cardinality 2. And if you do this, you get a bigger FMEA table with, as you can imagine, also combinations of faults like failure of the 2 generators are possible explanations in this case. And you can import the FMEA table in a spreadsheet and view it in a spreadsheet. So we have some time. Skip some time so I can demo the part on TFPGs. So as I said, TFPGs are a model for fault propagation. This is an example of TFPG. It's a formalism, classical formalism taken from the literature. So the idea is that you can specify faults and anomalies in the system. So anomalies are called discrepancies, and you can specify how faults propagate in the system. So here in gray we have these boxes which represent the faults, the basic faults, generator 1 dead, generator 2 dead, and the same for the 2 sensors. And in yellow, we have some discrepancies, like B1 low means the voltage of battery 1 is low, and S1 wrong means that the output of sensor 1 is incorrect. And the arrows represent propagation from faults to discrepancies or from one discrepancy to another. So for instance, this arrow means that failure of generator 1 may propagate and cause a low voltage of battery 1 within 5 to 8 time units. This star over here is just a specification of the possible system modes in which this propagation may occur. In this case, star means all the modes. Here we have another example. So B1 low may propagate and cause output of sensor 1 being wrong within 2 to 3 time units, and this may happen only in primary and secondary 1 mode. So basically we have these modes, primary, secondary 1 and secondary 2, which represent the different possibility of connecting the batteries to sensors. And here, secondary 2, in mode secondary 2, this propagation cannot happen because in mode secondary 2, battery 1 is disconnected from the sensors. Last thing, you can specify either or semantics for the propagation or and semantics. So or round circles means that either of the input propagations may cause the activation of the discrepancy, whereas and means that all of the input propagation have to take place in order for the anomaly, for the discrepancy to be activated. So in this case, system can become dead only if both these two anomalies happen in the system. So both sensors produce an incorrect output. So as you can see, the TFPGs allow to represent temporal dependencies between events in the system, mode constraints, and delay bounds. So we have a few analyses that we can do using TFPGs. So we can analyze TFPG completeness. So basically, this means that we want to match what is specified in the TFPG against what is specified in the system. So the question is whether all possible failure propagations which are specified in the TFPG, which are specified in the system, are captured by the TFPG. And the second question is tightness. So assuming we have some time bounds and modes in the TFPG, we want to make sure whether these time bounds are precise. So and whether they can be made more precise without losing completeness. So something like increasing a lower bound and decreasing an upper bound. So let me go to the demo. So one thing which I also want to mention is that it is also possible to automatically synthesize the TFPG. So we have these two use cases. Either the user specifies the TFPG manually, and then it is possible to validate the TFPG with respect to the model, or alternatively, it is possible to let the tool automatically synthesize the TFPG given a specification of the faults and of the discrepancies. So, first of all, so I have modeled a TFPG called expected TFPG. This is one which we have modeled manually, and we have a graphical viewer for the TFPG. So, for instance, this is what you can see using the TFPG viewer provided with xSAP. So these are the different faults and discrepancies, the arrows. So you can click on an arrow and you can get the details on the source and destination nodes and on the time bounds. So here, for instance, we have this propagation bound, which is exactly 2 time units, and the modes. So this is the TFPG which we have modeled manually. We can do, as I mentioned, different analysis. For instance, we can validate this TFPG against the model. So we have this script called validated TFPG behavior. The inputs are the SMP model and a list of associations. So the idea of associations basically that you want to associate TFPG nodes with states in the system. So in the TFPG you have nodes like voltage of battery 1 is low, and then you associate this with an expression of the system model which states that the voltage of battery 1 is low. So the association file provides basically the link between the TFPG information and the system model. So here we are validating the completeness of the TFPG. We can specify some bound. It's also possible. We also have some routines that do not need to specify a bound. In this case, we're just checking the completeness using boundary model checking. So the analysis is running, and while the analysis is running, I'm just giving you some additional details about what it means to validate completeness. So basically, you have say this part of the graph, and completeness means that, for instance, you want to be sure that the firing of this node S1 wrong is always preceded by one of these two nodes which are linked to this anomaly. So this is what is specified in the TFPG, and you want to make sure whether this is also the case in the system model. In addition, you also want to make sure that the mode constraints are respected. So here you have PS1 and S2 as constraints on the propagations, and also the time constraints should be respected. So here this propagation should happen between 2 and 3 time units, and here between 1 and 2 time units. So running the analysis, we are checking whether these failure propagations that are possible in the system are correctly captured by the TFPG. So this check is realized internally by translating these constraints into a set of proof obligations. And these proof obligations are automatically checked by the tool. So as you can see, in this case, we had to check 18 proof obligations, and all of them are satisfied within the given bound in this case. So the TFPG is complete with respect to the model within the analysis bound in this specific case. And similarly, you can also check the tightness of the TFPG. So here we specify edge tightness as parameter, and you can do a similar analysis. And edge tightness means that you want to analyze whether the bounds, the time bounds can be made more precise. So for instance, let's say here we have this propagation which is specified to take place between 1 and 2 time units, but perhaps this propagation, perhaps we have this more precise bound, which is 1, 1. So, and of course you want to make time bounds more precise, but without breaking completeness of the TFPG with respect to the model. So in this case, we are running this analysis, and again, we have a set of proof obligations that are being checked. And if all of them are satisfied, then we get this result that the TFPG is tight with respect to the model. We also have additional analysis. There is an analysis called tightness, which means that we can actually synthesize the tight time bounds. So we can give the tool as input a complete TFPG, and we can have the tool automatically synthesize the most precise bounds. And finally, we also have the possibility to automatically synthesize a TFPG using this script called the synthesize TFPG. And as input, we have to give the tool the system model, the extended system model, and the list of associations. So basically, we provide the nodes of the graph, and we want to synthesize the errors and possibly the time bounds. So if we run the synthesis, then actually the synthesis is based on internally on routines which are based on full tree analysis. So this analysis it's basically a causality analysis which is carried out for each of the nodes, and then as an additional optional step, the most precise bounds can be synthesized. So I just synthesized the FPG, and then we can view it. I think here it is out. TFPG. So here, this is the automatically generated TFPG, and it has basically the same shape as the TFPG that we expected, but here the time bounds have not been synthesized. So 0 minus 1 means 0 plus infinity. So I did not synthesize the time bounds, but as I mentioned, we have a specific analysis which enables you to do this. So you can also synthesize the bounds on the edges. So I think this concludes the presentation. So if you have questions, please feel free to ask them.
Okay, thank you very much. Are there questions from anybody? If not yet, I mean, we have of course the recording, and I'm sure once we are talking about the real integration of all these tools, then there will be more questions. So the last topic of the agenda for today is the presentation of the TESTONA tool from Bernhard Mattner. So I think I can give the ball to Peter, right? Peter?
Yeah, hello. Hello, everybody.
Okay, so I give you the ball, make you the presenter, and then we are looking forward to see the TESTONA tool.
Yeah.
Okay.
So okay. I prepared you a short set of slides here, giving you a short idea what is the TESTONA tool. We will today focus on the tool integration aspect. TESTONA is a test design tool. Okay, this is me. You might be familiar with the general test approach, testing theory. You have test planning, test design, implementation, test execution, and evaluation. Before you can start testing, you hopefully have some kind of specification. This might be requirements document. This might be formal specification. This might be, if you are in agile development, you have some user stories, epics, feature requests, these things. And if your testing is then done, you have a tested subsystem. And TESTONA focuses basically on the test design aspect, because here the essential part is done. You decide how many test cases you need, what are your test goals, etc. TESTONA relies on the classification tree method. This is the systematic process for black box testing typically. I have a short example which we go over just quickly because you are today interested into the tool integration aspect. The first aspect here in the classification tree method is you select your test object. For today, I brought you a database management system. You have a client-server application here. This can be any kind of system. This can be embedded systems, security-related, safety-related systems, processes, physical systems, etc. And for today, we go for this database management system. You typically have then an input data space. For our database system here, we have browsers available. We have different users. We have delete, create, modify operations, etc. This is the case for any system under test. You have an input domain, input data space. You have an environment your system is operating in. You have to consider that. And the classification tree method then suggests you introduce relevant aspects. You introduce those parameters you are interested in. I have identified here different user privileges. There's different operations on the database. As I told you, create, modify, delete. And there's different access methods, and then the classification tree method suggests that you write this nice tree structure for all these aspects. So for operations, you have then 3 values, and if you then combine all these individual aspects into a classification tree, then you get this nice matrix where you can specify your test cases. This is the classification tree method. This is quite straightforward, and using these steps basically enables you to identify test goals, reliable, standard, conform, and reproducible. And if you then go one step further and do not combine these aspects by hand, because all these things we've just seen here can be done using a pen and a paper. But if you want to go a little bit further, if you have realistic systems and not these sandbox examples here, you typically go for the automated test generation of TESTONA, and then you have nice things such as equivalence class testing, boundary value analysis, combinatorial testing you might heard of, which have this all pairs testing, which is the most common one here, We have also prioritized some statistical testing available, so we have a long list of features that can be used then with TESTONA. And TESTONA then gives you test efforts, test suite sizes, the amount of test cases you need to implement for your system to be tested. So TESTONA, what is it? Well, TESTONA is then the graphical editor to support the classification tree method. We have this test case generation with generation rules. We have verification of test cases against the dependency rules. We have tag approach. You can annotate any kind of metadata. And this is interesting for today. We have a generic and customized tool coupling. This is a short list of customers we already have, and we want today focus on the tool integration. I will also give you a short tool demo on this tool integration, so you all get an idea what we are actually doing. So technical features here, tool integration. The TESTONA tool itself is an Eclipse application. So we can import here features from AUTOSAR. If you're in the automotive domain, you might know that AUTOSAR is a standardized specification and implementation approach for systems in the automotive domain. You can import any kind of mind maps, and you can also import specifications, also product families from Meran. The first two are working file-based, so the AUTOSAR import is working on the AUTOSAR XML, also mind map files are typically XML files. For Meran, we have a direct database access. We can output and export to Microsoft Word and HTML, which is also file-based. And we have support for the Messina tool. Messina is the burner and Matter hardware-in-the-loop system. Hardware-in-the-loop systems are typically found in the embedded domain, such as automotive, aerospace, and others, where you have integration levels, where you have your embedded control units run against real sensors and hardwares, and you have then the hardware-in-the-loop systems, and Messina here is the front-end software for that. We have bidirectional import and export with the MATLAB tool, working file-based. We have Excel, which we support reading and writing. We have DOORS support, IBM Rational DOORS, where we are using the client-server architecture of DOORS. We have support for HP Quality Center, which is now called HP ALM, stands for Application Lifecycle Management, where we're also using the client-server infrastructure. We have support here for the test idea and for MTest. We also have support, not listed here, for the VectorCast environment, which is a unit testing tool, which all works file-based. And the TESTONA tool itself, well, it uses XML files. The TESTONA XML files are self-contained. TESTONA can be used from the command line. We have command line interface available, which is especially interesting if you use TESTONA in tool chains. TESTONA itself can be used remotely using a Java RMI, remote message invocation, which is a Java way of accessing applications remotely. And finally, TESTONA itself is an Eclipse RCP application, so we support the integration of the TESTONA features into other Eclipse applications. This could be a way to go also within AMASS, so we need to see what we can do there. So for today, what I can show you is, well, the file-based exchange is not that spectacular. We have import and export facilities using the corresponding file formats like Excel, like HTML, and others. I would like to show you today how we integrate, for example, with IBM Rational DOORS and also with the HP Quality Center to show you our understanding of a seamless integration to get this experience of an integrated approach from the end user's perspective as smooth as possible. So we will switch over to the classification tree editor, to the TESTONA tool now. And this is the TESTONA tool. Let's for now hide these aspects. The TESTONA tool itself is a common application. You have this file menu, edit menu with clipboard access, undo, redo. You have the diagram where you can format the aspects here in the tree. You can have different fonts, font sizes, colors. You can have these elements bold, italic, and so on, which is quite the same as, for example, with Microsoft PowerPoint. We have the toolbox containing the TESTONA specific parts, where we today are going to have a look into the Quality Center synchronization and also into our requirements interface. We might have the time for the code generation also. I have some slides in the slide deck. If we have not time for that, then we can talk about that in another session, for example. Window, well, yeah, you can arrange all these elements. We have an online help, a welcome page, an about box. It's also not that spectacular. The classification tree itself here is containing basically the aspects I want to consider in my test cases. I have an outline view here on the side, and here these are the test aspects. They have different privileges, operations, and so on. And what I have then down here is I have different test cases. So in this first test case, for example, I have here the administrator user performing a new operation, and he's using a native tool. The choices within the classifications are exclusive. So I have either an administrator or a regular user, but at no given time the two of them. I can either perform a new operation or an edit operation or a delete operation, but not all the three at the same time. And the same for the access method. I have a native tool, or I have any kind of browser, which can be Firefox, Safari, Internet Explorer, and I have a programming API. This item here, I will just delete it to remove it. Okay. So this is a really short introduction into the TESTONA tool, and then now the question is, how can this integrate with requirements? How can this integrate with also safety-related requirements? Let's just step to the slides for this. We have the case that basically requirements, we have it here in the DOORS example, but it works with other requirement management tools as well. Requirements are basically a list of natural language aspects which we want to test in our case, and then we have test cases within TESTONA. And what we have here is a certain mapping from requirements to test cases. We will just do it within TESTONA. You can see how these functional requirements are then related to test cases. Once you have this, you can use this, of course, also for requirements coverage analysis. In this small example, you can see that requirement number 2 is not tested at all. This is a little bit problematic. We can see that requirement number 3 is tested more than once. Requirement number 5 is tested. And we have the strange situation that test case number 6 tests 2 requirements, requirement number 5 and 6, which can be problematic because if test case number 6 then is failing, we do not know whether the reason was the failing of requirement number 5 or number 6. The nice thing I also would like to show you is that the tracing of requirement changes. So we will have a look what happens if requirements are then deleted, if they are modified. How can I then recognize this in terms of my test specification and know which tests need maintenance efforts or not. So for this to work, I have this TESTONA example here. And I already prepared this thing. Just close it here. I have these requirements interfaces. I can use requirements from IBM Rational Doors or Microsoft Access. We recently added support for requirements for HP ALM Quality Center also. And I have here now opened a Doors connection. And in the Doors connection, well, I have modules and projects and folders, as you might be familiar with. And here I have, for example, some English folders and projects. And in this thing here, I have a module, this then loads, and this is the view which I have in TESTONA. I have an online view on the requirements. I can scroll through them. I have support for the different views. So you might be familiar with DOORS that you have different columns, that you can have filtering and other aspects, which is all offered by the IBM DOORS mechanisms here. We recently added the feature of baseline support. So you can then have these requirements in TESTONA, and what you then can do is you can use these requirements and assign them to your classification tree. How you do that, you take a requirement with your mouse, you drag and drop it right there where it belongs, and let's assume this requirement works on the normal user. Requirement number 12, then we scroll a little bit through and use requirement number 14 on the administrator user, for example. You can then use this requirement for the new operation, this requirement for the edit operation, and so on. So what we then can see is that, for example, this new operation now has a property of a requirement with the ID number 429. This is attached to the new operation. What we also can do is we can then filter and see which requirements we have used. We have used 4 requirements here. We can see the requirements which we have not used. And we can also have a graphical representation. You can see this in bars. In the middle, we have the requirements, and you can see that these requirements have been used in some test cases. You can also then have this in a matrix view. You can see, okay, you have then these requirements covered. We have the requirements here in lines, and we have here in the columns the elements in TESTONA, and can see then which requirement has been used. So then now the interesting part is what happens if these requirements changes. And I will just now do some changes. I have opened here my DOORS client. I have here a very old DOORS client because I have a local license here. We support any recent DOORS installation from DOORS 7 to DOORS 9.6. And I will now open the DOORS module which I have used in my TESTONA example. And here is the doors view as it is in the online client. And what I will do is I will change, for example, this requirement with ID number 12, classification tree method aims for tra-la-la-la-la-la-la. And what I will do is I will just insert here a single word, so it is not based on, let's assume this is the change I make here. What I also will do is I will, for example, delete this requirement with the ID 429, just remove it. So for now, the changes here are only in my doors client. They are just locally in this view. They are not persisted in the database. And what I now do is I save these changes to the database. It takes a short moment because doors is slow, even in local installations. Now it has been saved. And what I now can do in TESTONA is I can synchronize. I can see what happened. And it takes some moment and then I see, okay, what has happened. I can see I have yellow changes and I have red changes. The yellow changes were edit operations. The red changes were delete operations. So let's just see what happened. We only have a look into the changed requirements. And here we have the requirement number 12. We have here the new text, which says it is not based on, and we can see here the old text, it is based on. So we can really see what has happened on the database, what changes had been made. And let's just assume that here now it means that we now perform also a change to this parameter. So now the test specification again is in line with the functional specification, and I will locally accept the change. Here we have a requirement which has been deleted. It's attached to this new parameter, so this is no longer part of the specification. It is obsolete. So what I will do is simply I will delete this element from the classification tree and also remove this change here. And now I have a single change here, which is a reported change because all these elements here have an element within ID 429 no longer existent, so they are now listed here. This used to be a bug in this version. We have already fixed this in the upcoming version. So let's for now also accept all these changes. Yes, accept these. And now my test specification is again in line with the functional specification. So here I always have then an updated view. I know when there's requirement change, when there's changes to the space, so these safety specific aspects, what do I need to modify also in terms of testing, in terms of traceability, in terms of test and the requirements coverage. So this is really helpful here. What you can do is that you can export now the specification you have in TESTONA back to doors. I will show this to you using the other doors installation. This is the newer version, and what you can do, you can export these test specification to doors, and then you need to specify which is your doors connection. You select which path in the tree you are using. For example, you can now export this, let's assume, to this element. You need to select the root node for the test cases. And then you need to establish here a mapping. We can here say that we have the test names mapped to the doors object headings, that we map some tags here to the object tags and so on. And then you can actually export it. You can create linkings as well. You can create incoming or outcoming links in a certain link module. And then you have these test cases export to doors. So this is a distinct export. And we also offer the way of actually synchronizing this. And this I will show you using then the Quality Center example. So this was really fast way through these features. What have we done? Well, we have had a list of requirements in doors. We have then dragged and dropped them to the test cases and elements in TESTONA. So we have performed this linking. Once we had this linking, we were able to do some filtering. We could show what are requirements already used, what are requirements not yet used. And we had already seen that we have this tracing of requirements changes, so we can easily see if we were affected of changes or not. We have specifically this situation. If you have, for example, a manufacturer and a tier 1, for example, so you have contract situation where you have then one party defining the contents of what is to be developed, and the second party then doing the actual development where you have some changes, change requests, etc. And then have really here a good overview for this test specification and functional aspects. Really helpful. We are using here the way of the doors DXL scripts. So to have this working, you require a locally installed DOS client on the platform you are working on. So this restricts the usability of these features to the Windows environment because DOS clients are only available in the Windows environment. If we go for the HP Quality Center, which is now known as the ALM, what is Quality Center? Quality Center is a test management tool. It offers release and lifecycle management, requirements management, test plan, test lab, defect management, and reports. It offers tracing between requirements, test defects. You have change impact reports, and so on. And from TESTONA, you can then synchronize your test plan, your test design also with the HP Quality Center test design. And we will have a quick look into that as well. So we have here, again, our TESTONA. And we will now use the Quality Center synchronization. I will establish a new synchronization. I can connect here to a certain Quality Center server. Let's just see if this works. This is not correct. So I will now log in into Quality Center. I have here some domains and projects available. Again, I need to establish a mapping. I have here TESTONA file opened. I could also download it directly from Quality Center. Then it is loading the project structure out of Quality Center, and it does not work. Oh, then I used the wrong database. Let's just do this again. Ah, we have it here, okay. That works, yeah. And I also wanted to show you what we did here in terms of mapping of these attributes and how this works. I have no access currently to this Quality Center server because it requires an old version of Internet Explorer, which I do not have on my system, so I can only show you the TESTONA side of this. For Quality Center, I recommend you to have a look on the HP Internet page then. So what I will do is I will then establish a new synchronization here. I will connect to this server again. Will not save the password. I have Quality Center version 11 here. Connect to the server, use the local file, then it loads the folder structure out of Quality Center. And what I will do is I have then the subject that it is called in Quality Center. I have several projects here. I will use this project. And from this project, then I can specify a mapping. I will just use a simplified mapping. I will have all these mappings created automatically. In Quality Center, you have these things called attachments, comics, creation dates, description designer, and so on. I will just have these created automatically. We'll then have here also the file attachments created properly. And then I can press finish. And then it loads all the test cases, all elements from Quality Center, and it provides me here an initial synchronization. And the synchronization is similar to any kind of synchronization perspective you might know from Eclipse, you might know from SVN, from other versioning control systems. This takes some time, and here then again can filter and show the outgoing changes. I have here some test cases which are only present locally in my TESTONA instance. I can see the incoming changes, where you can see what are the current values in TESTONA, what are the values in Quality Center. And what I then can do is I can check out these elements. I will just do it. I will then check them out to have these locally. And you can see then these elements are created here in TESTONA, and they have their corresponding tag values. So this is typed manually, it has test case name, it has a status, and so on. All the values which we have in Quality Center as well. So the synchronization, then if I now resynchronize this, then these elements 50, 49, 48, and 47 are no longer shown because they are present then in both domains, and then I can make changes to these which are then committable to Quality Center. If there's any change in Quality Center, I will see this locally. In this short example, I have no support for these question marks and other marks here because this is just a sandbox example. In the real running example, then we would also see these elements. So then you can have test frames created in Quality Center, specify these test cases here in TESTONA, commit them back to Quality Center, have also the requirements interface from Quality Center. So you have then really a good requirements coverage. You have then the seamless integration from the Quality Center features within test design with TESTONA. You can commit them, synchronize them back and forth. We have seen this for the quality center just here. We have seen it right before for the requirements interface. So this is for the client-server aspect. Just to show you where the other elements are we found, we have import facilities here. For example, you can import Microsoft Excel files and customize that. You can import mind maps. You can import test result files in a comma-separated or tabular-separated value files for the annotation of test results. So what is test result? Well, you can annotate for any test if it passed or failed. You can also import this information from Quality Center. I have 3 more slides on that, which I will show you shortly. We have, of course, the export facilities. We can do code generation. I think we will not cover that today. We have export to Excel, HTML, PDF, RTF files. We have export to DOS. We have export to MATLAB, etc., which we think is quite complete. So we just saw here the integration of TESTONA with the test plan module of Quality Center. Requirements management works the same as we've just seen it with DOORS. We have synchronization, we have change management. What we can do is we can annotate test results. I have talked about that, which can also be imported from Quality Center. Otherwise, it can be imported from text file or Microsoft Excel files. And if we then have this, we can use the test results for some root cause analysis. So we can then see, okay, if these test cases failed, we can then look for the common configuration within these test cases. And for example, in this case, we can see that whenever the light switch is turned on, whenever this configuration is triggered, then we have a failure in these tests. Whenever the light switch is off, which are the other cases, then the test passed. So there seems to be a problem now with this light switch parameter. This information here could be obtained from Quality Center or from external files. We've talked about the Excel import, where we also need to establish this mapping. In this case, we have in the Excel lines, we have the test cases, and in the columns, we have the parameters. It might be that the case is vice versa. You can configure whether each column is a parameter or a heading or a test case name and so on. So what we've learned from all our imports and exports and integrations is that you need the user of your tool, that is, the user needs to be able to customize the mapping, because you have many different Excel files, you have many different DOORS configurations, many different configurations of your Quality Center servers. So this is very essential. We've learned that you are able to customize. It's just that the mapping needs to be configurable within your application. Otherwise, this is not really useful. So once you do the Excel import, the nice thing you can do is you can do things like test coverage, test completeness, etc. Can have a look into that. For today, I brought you also test implementation. So consider that you have now finished the test implementation. The question is, how can you then have these test cases executable? So consider the situation. You have created a classification tree, have done your test design, based on some functional requirements, based on safety requirements, for example, and now want to execute these test cases. And what we suggest is that we have here a generic code export. How can this work? I will give you a short example. I have here an example for JUnit, but this works for any XUnit, PUnit, CUnit, whatever. It works for any XML, for any textual specification. And what we suggest is to annotate code snippets to the individual parameters in the classification tree. So here I have an example with speed and gear and list. So it seems to be an automotive example where we have different speeds and a gear you can select. And to translate these parameters into something executable, well, there's a set speed method in our system under test. There's a set gear method and a set something method. So we do this for the input parameters. And for the output parameters, we use some assertions here. Assertions is the way of comparing things in unit tests. So we get from the system the status of the LED, and we get from the system the internal Boolean variable whether the test was successful or not. And we then compare it against the selection we had in the classes. So for the first test case, we would assume that the first LED is then be turned on and the test was successful. The second, we expect the third LED to be turned on and the test was successful. In the last test case, we have the LED number 2, and we consider that something went wrong so that this assertion does not hold. But to make these things executable, we need a frame per test case. So what we do is we suggest that we have a short code snippet defining what is the signature of a test case. We have this public void, which is the general specification for unit tests. And we then use here this variable, which is translated to the test cases here from our actual specification. And to have it runnable, then we need a general frame. So we need to make some import declarations and specify a class name. And if we do all this, then we get a test case in the end, which is executable. So we have then a unit test example. We have some imports. We have here the class specification. We have some general initialization and setup. We will skip that, and then we have here actually a test case. This is test case number 1, throws exception. This code comes from here. We have set speed, set gear, set something, which corresponds to slow, third gear, and we pass here an array, for example. And then we have the assertions where we check if the LED is flashing or not, and we check whether it is successful and true. And then the same for the third and second test case, and so on. We think this is really beneficial because you only need to specify these aspects here per parameter. You do not need to program any single test case. You can write the requirement IDs directly to the test case, so you have even your executable test scripts directly traceable to your requirements, to your safety requirements, which is really nice. I have shown it to you for the JUnit example. It also works for some XML standard here. I've just invented some XML called test bench, where we have test case, test steps, and so on, when this is another syntax. And what you can do, of course, is you can imagine any textual syntax. If you can script your system under test or your test environment, then you can use this approach and actually generate executable test specifications, test implementations directly from TESTONA. So I would just close for today showing basically this slide. We do not have that much time for questions and answers.
Yeah, thank you very much, Peter. I think this is really cool. I mean, we were able to have all these presentations exactly in the time frame that we planned, and I found them also very impressive, especially with regards to the existing integration capabilities. So I think we can. There are some very good possibilities to integrate some of these existing AMASS tools together. And of course, also general ideas how we can design the AMASS platform so that real seamless work is possible. So I think today we have seen some very good examples of being really seamless to the user. So that was very good. Are there specific questions to Peter's presentation?
Hello, this is Angel from Technalia. I have a question for Peter. Can you tell me if your solution of TESTONA is based on files or you have a database?
TESTONA itself uses these XML files, which are stored locally to the file system of the user. We are considering to offer here some SVN support, for example, other things, but in the end, TESTONA files are XML files, so those are most flexible from our perspective. So we do not yet have a database integration. That would be something really beneficial from the AMASS project, for example, if we consider that we need a database in the end, that we need some general SQL, for example, that could be really something TESTONA is benefiting from.
Okay, thank you.
Any further questions? If not yet, then I would try to make this recording of today's session available to all project partners. Thank you very much for participating and presenting today. And be reminded that we have another session on 23rd of June, which is Thursday at 2 p.m., where we see some other interesting tools of our partners. So, of course, everybody is encouraged to participate also in this session. Yeah, so that's it for today, and thank you and bye-bye.
Thank you.
Thank you.
Bye.
Thank you.
Bye.